This tutorial will show how to start a model in PERFORM-3D. Perform offers two ways to start the modeling process: directly in PERFORM-3D or by importing data from SAP 2000, which we will show first. SAP 2000 can export geometry, materials, sections, and loads to PERFORM-3D. In SAP 2000, we have previously developed a one-bay planar frame, 10 feet by 10 feet. It is framed with W18 by 50s and has a fixed restraint at the left support and a pinned restraint at the right support. In addition to the self-weight, the frame has a small lateral load of 25 pounds and a trapezoidal live load on the beam. Note that the units are set to pound-feet. SAP 2000 allows the model to be exported to PERFORM-3D by going to the File, Export command. However, note that the commands for exporting to Perform are grayed out. This is because an export can be done only if an analysis model exists. So we will run an analysis. After the analysis completes and the analysis model is created, we have two options for export. One is a text file, which sends out just element connectivity, and the other sends out the entire structure in PERFORM-3D's native file format, which is the option we will choose here. The transfer form lists the items that are and are not transferred. Many of the nonlinear items supported by PERFORM-3D can only be defined once in the Perform program. Clicking the transfer button will send out the model. Now we will open the SAP 2000 file in PERFORM-3D. With PERFORM-3D running, we will open the SAP 2000 model just exported. Remember that our model directory was SAP2Perf, which stands for SAP to Perform, and also that the model was created using pound-feet units. Note the structure description written out by SAP 2000. Perform commands may be accessed through the menu bar or the toolbar, and we will typically use the toolbar. When working in Perform, you will be in either the modeling, also known as building phase, where the model is created, or in the analysis phase, where the model is analyzed and results processed. The buttons following the phase buttons are context sensitive, meaning they are dependent upon the phase selected. For this tutorial, we will work in the modeling phase. Next, we will take a look at a number of the buttons or tasks associated with this phase. The umbrella is the symbol for the overall information task and is the screen that is first displayed when importing the model. The nodes task is where nodal data is specified and where the model may be displayed. In the lower left corner are the view controls: Basic, Plan, H1, and H2 are the standard views. The V and H1 angles may be varied to set other displays. In addition to the Nodes tab, there is the Supports tab, which displays the fixed condition at the left support and the pinned condition at the right support. There is also a Masses tab, where the member masses are shown lumped at the nodes. With the display in weight units, the masses are shown as approximately 500, or 50 pounds per linear foot times a 10-foot tributary length. We can also switch to mass units. The next task is the components task. This is where both linear and nonlinear components are defined. And it is on this task that you will often spend the majority of your modeling time. For our imported model, we switch to the Cross Sections tab and select a type of beam, steel type, non-standard section. Perform considers the section non-standard because it was imported from outside the program. If we select the W18 by 50, we can see that all the dimensions and properties were imported from SAP 2000. Also note the naming convention. The name starts with XEC to denote that it is a cross-section component. Selecting the Inelastic tab and then a type of FEMA beam, we find that Perform has generated a FEMA beam component based on our imported W18 by 50. Note that the name starts with INE for inelastic. Next, we select the Compound tab. It is on the Compound tab that the various components are assembled. If we select the type of frame member compound, and then the non-FEMA column that has been generated by Perform, we see that this compound section consists of one W18 by 50 cross-section component column with a relative length of 1. The FEMA compound column component consists of two inelastic components, each with a relative length of 1/2. We can add additional components to the compound section by clicking on the Component Type drop-down list. Switching to the Self-Weight tab, we can verify that the self-weight is 50 pounds per linear foot. Next is the Elements task, where the sections defined previously in the Components task are assigned to the model. Perform has defined two groups based on the SAP 2000 model data, one for columns and another for beams. As we switch between groups, note that the highlighted elements change. With the current group set to columns, clicking the Properties tab, and then selecting a highlighted element by clicking on it, displays the assigned component, in this case, the compound column section with the cross-section component. If we go to the beam group and then click on the beam, we see that the beam has been assigned the compound beam component. Selecting the Orientations tab displays the local axes for the group. The Frames task allows us to display a subset of the overall structure. However, in this case, since we did not define any groups in SAP 2000, the only frame defined in Perform is for the entire structure. Next, we move on to the load patterns, which is the last task that we will cover in the modeling phase of our SAP 2000 model. On the Nodal Loads tab, 3 patterns have been defined. One for our lateral quake load, which shows the 25-pound load at the top right joint, and 2 more for acceleration in the X and Y directions, which are simply the mass times an acceleration of 1. Clicking the Element Loads tab shows that one element load pattern is defined for our live load. With the beam element group selected, we can click on the Add Loads tab to see that the trapezoidal load has been applied. Switching to the column group, we see that no columns have been loaded with live load, which is correct. Note that the colors of the elements indicate the status of the loading. Clicking on the Self-Weight tab shows that the dead load pattern has come over from SAP 2000 as self-weight, which again is correct, and that both columns are loaded. If we switch to the beam group, again we see that it is loaded with self-weight. Clicking on the Plot Loads button shows how the self-weight has been distributed on a tributary basis to the nodes. This concludes our discussion on starting a Perform model by importing a SAP 2000 structure. We will next start a model from scratch in PERFORM-3D. When starting a new model, the first task is to fill out the overall information page. We will call the model Frame, as we wish to define the same model as imported from SAP 2000. We will set the units to pound-feet and add a brief model description. Next, we will move to the Nodes task. Starting with the Nodes tab, we will define our nodes using a grid. Our planar frame is to be vertical, and we wish for it to be aligned along the H1 or x-axis, so the offset angle will be 0. The starting location will be at the origin, so all coordinates will be 0. The frame has one bay and one story, with the width of 10 feet and a height of 10 feet. We click the Test button to see the layout, and it is correct, so we click OK. Next, we select the Supports tab and select the lower left-hand joint. This node should be fixed. So we set all the supports to fixed and then click Test. Again, followed by OK. The lower right-hand joint should be pinned, so we fix the displacements but allow the rotations to be free. Again, click Test and then OK. On the Masses tab, we will define the masses. We start by defining a new mass pattern, which we will call nodal mass. Using weight units, we input a value of 500 or 50 pounds per linear foot times a tributary length of 10 feet for H1 and V, noting that H2 will be the same, and then select the top two nodes. Click Test to verify, and then OK. Selecting the Mass Units option displays the values as expected. Before moving to the next task, we will save the model. Moving on to the Components task, and as mentioned earlier, this task can require significant time when doing large and complex nonlinear analyses. However, we will keep it simple in this model in order to emulate the data brought over previously from SAP 2000. We start by selecting the Cross Sections tab. Here is where we will define the section properties. Starting with Type, under the Beam sections, we will select Standard Steel Section. By using a standard section, we can pick the section from the library built into the Perform program. This differs from the SAP 2000 import, where the properties came over from SAP 2000 and thus were called non-standard. For the name, we will use Beam W18 by 50. And then in the standard section area, we will select the AIC type and then the W18 by 50 section. Note how all of the dimensions and properties have been filled in except for the shear modulus. The shear modulus is a calculated value based on the material stiffness and will be determined after we do the next step. The inelastic strength tab is where ultimate strengths are specified when developing inelastic beams. The elastic strength tab is where strengths may be specified when using strength limit states. However, for this tutorial, we will skip both of these options. The last step in this section definition is to click the check button. Note that the shear modulus is now calculated. Because we have no errors, we will click the Save button. This section has now been saved. We will now repeat the process just done, but for the column. This time, we will use the name column W18 by 50. And again, we will select from Perform's standard section library. With no errors, we click the Save button. We have now defined the two cross sections in our model, one for the columns and one for the beam. In addition to these cross sections, Perform offers many other component types. The Inelastic tab is used to specify nonlinear components, including FEMA beams and columns. But we will skip this tab as our model is elastic. The Elastic tab is where elastic components such as end zones and releases may be specified. But again, none of these are needed for our model. The Strength Sections tab is where strength limit states can be defined using capacity factors. The last tab we will visit in the Components task is the Compound tab. It is on this tab that we can assemble multiple basic components into a single compound component. For our model, we will set the type to frame member compound. Starting with the beam, we will create a name and then move over to the Basic Components tab. Clicking on the Component Type drop-down list, we select the Beam Standard Steel Section option. This results in the component name drop-down list being populated with the Beam W18 by 50 section we previously defined. There are a number of different ways to specify the length of this component, and we will use the proportion method. In this case, our length value will be 1, as the cross-section is the entire compound component. Clicking the Add button adds this component to our list. We could add additional components to the list up to a maximum of 12. If we were setting up limit states, we would visit the Strength Sections tab. And lastly, we will enter the self-weight of 50 pounds per linear foot. We click the check button and note how the status window is updated. Click the Save button to save the beam compound component. Next, we will repeat this process for the column. Our components task is now complete. The next task we will visit will be the elements. This is where we will assign the compound components we previously defined to the model. We start by defining two element groups. One for the beams. We will have no geometric nonlinearity. And one for the columns. This information shows up on the Group Data tab. Next, click the Add Elements tab. Set the current group to beam and select the straight line option. Click the top two nodes. The tab should show two nodes selected and one element added. Click Test and then OK. Switch the current group to column and select the grid option. Click the bottom two joints, followed by the top two joints. And click Test. If not correct, click Undo and try again. Otherwise, click OK. Select the Orientations tab and switch the current group to beam. The beam member should be light blue, indicating that it belongs to this group. Select the beam, which turns red when selected, and choose the vertical up option. Click Test and then OK. Switch the current group to column and select both columns. Choose the plus H1 option. Click Test and then OK. We have added the local axes. The last tab we will use will be the Properties tab. With column showing as the current group, select both columns again. Because we have not yet assigned a component to these elements, type should show as none. Click the Assign Component button, and for type, pick the Frame Member Compound option, and then column for the component name. Click the Show Properties button to verify the column compound component. And then the Assign button to assign. Switch the current group to beam and assign the beam compound component in the same manner as done for the columns. We are now done with the elements task. Components have been assigned. The last task we will visit during our modeling will be the load patterns. With the Nodal Loads tab selected, we will define a new pattern named Quake. Select the top right node, and we will input a force of 25 for H1. Click Test, and then OK. Select the Element Loads tab and define a new load pattern named Live. Select the beam element group and then click on the beam. The beam turns green to indicate that it will be added to subgroup 1. Click the Done button and then click the Add Loads tab. For subgroup 1, the load type will be a gravity distributed load with a starting magnitude of 0 and an ending magnitude of 10, and the entire length of beam will be loaded. Click the OK button to apply the load. Select the Self-Weight tab and click the New button to add a pattern called Dead. Starting with the beam element group, select the beam member to indicate that this member should be included in the self-weight calculations. Switch to the column element group and select both columns. This will include their self-weight. Click the Plot Loads button, and we see that the tributary nodal loads for self-weight are as expected, namely 500 pounds at the top 2 joints and 250 pounds at the support joints. The last step in our modeling phase should be to resave the structure. With the modeling phase complete, we have finished the bulk of this tutorial. However, we will take a brief look at the analysis phase just to get a sense of how to proceed with the analysis. We start by clicking on the Analysis Phase button, which brings up a new set of task buttons. Note that these buttons are blue versus red for the modeling phase. The first task we will look at will be load cases. Perform has a number of load case types available for sophisticated analyses, but for our simple model, we are looking to do only a static analysis and will select gravity. We will name our new load case Live Load, as we will do an analysis with just the trapezoidal live loads applied. We will set the analysis method to linear and select Element in the load type options in order to use the live load pattern. We will use a scale factor of 1.6 to scale up the load. Clicking the Add button adds this load to the list. And we can click the Save button. We next move to the Run Analysis task. If so desired, we can click the Check Structure button to verify our model. Since it is okay, we will start a new analysis series. And we will name our series Live Load. And then enter a brief description. In addition to our static load case, The program typically generates mode shapes as well, and we will use a scale factor of 1 on our mask pattern, and we'll ask for 5 modes. Click OK, and under the gravity load case, we see that the live load is available. Click Add to add this case to the list. Note that the mode case was automatically added as well. We are now ready to run the analysis, which we do by pressing Go. The remainder of the tasks deal with results. Clicking the modal analysis task, we can view the mode shapes. Note that the modes were part of our live load series. Going to the moment and shear diagrams task, with the element group set to beam and the gravity loads on element option selected, we can click on the beam and then the plot button. This shows the applied trapezoidal live load with a maximum value of 16, or 1.6 times 10. Selecting the moment and shear diagrams option and then clicking plot shows the moment and shear plots for the element. This concludes our tutorial on starting a PERFORM-3D model.